I didn't. I know. That's Brocker's fault. Actually, it's Clancy's fault. Is Clancy even here?
What's my fault now?
We just had this great conversation about amputations and my knee surgeon wanting me to have surgery again tomorrow and all this stuff. And none of it was recorded. Some great stuff was said. And my logic,
entirely my fault. My bad.
Sarah even said my logic was flawless. I don't think she said that. She had the same eye roll my wife has. It's uncanny. The worst part is my wife is always right. She's like 103% accuracy rate. Yeah. So I just gotta ride this until it's Hey. Okay, so let's look at some of the missed questions from the midterm. Then let's look at the lab from last week, and then let's keep trucking. So actually, a funny thing is this very first question, dealing with write the necessary code to extract the 6. People gave me these like crazy dissertations where they were writing helper functions and all this stuff. I don't know, maybe I could have been more specific, but I gave you a list and I said, write the code to extract the 6. That's just cars and cooters, right? So, you come over here, I have this list. If I want to extract the 6 out of this, well, so if I take the cooter of this list, that's going to give me this. So if I take the cooter of that, that's going to give me this. If I take the cooter of, so then I have the list containing that. So then I have to take the car of that. That'll give me just this list. Then I take the cooter of that. That'll get me this list. Then I take the cooter of that. That'll give me this list. Then I take the car of that, and that'll get me this list right here. Then I take the cooter of that. That'll give me the list containing the list 6. Then I take the car of that. That'll give me the list 6. And then I take the car of that. Did I count one off? I have to walk through it again out loud. Cooter gives me that. The cooter of that gives me the list containing that. The car of that, actually I'm going the wrong direction, right? I'm going the wrong direction. So I'm going to take the cooter of my list. I'll take the cooter of that. So it'll get me this. I'll take so cooter gets me this. The cooter of that gets me this. I'll take the car of that, gets me that. Then I'll take the cooter of that, which will give me the list 4. Then I'll take the cooter of that, which will give me the list containing that. Then I'll take the car of that. That'll get me this actual list. And I'll take the cooter of that. That'll get me the list containing the 6. And then I'll take the car of that. And there's my list of 6. So wasn't that the last one I had? Oh, the car of that is the list 6, and then the car of that is the 6. So there's your 6. So just a series of cars and cooters to extract the 6 from this guy. Some of you did like the car of the car and the CDD, blah, 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 and that's fine. The problem with that is we do have limitation on how much you can do at once. So it's almost easier just to do whole cars and cooters. I don't know that anybody necessarily missed that. Just some people wrote whole functions that like extracted it as opposed to using cars and cooters to do it. So you did, I guess, more work than you needed to. Let's see, write a function named list of divisors that takes. So one issue that I would say kind of throughout the exam so, you know, the grades weren't bad. They were very polarizing, I guess. So, you know, most people either got 85 or higher or like below 50 or below 40. I think the lowest score was a 14. So there was a lot of the programming questions that were just left blank. So if the programming questions are being left blank, that means that you don't know how to write scheme stuff. And we've been writing plenty of scheme stuff by now that shouldn't necessarily be that difficult to write the scheme. And as you know, 400 level students, we should have enough background now to solve fairly complex problems, right? You know, not necessarily, you know, solve all the world's problems, but you know, I think most of these problems were fairly in the wheelhouse. But, you know, regardless. So, you know, if you were leaving programming questions blank, you really want to consider why you're, why? You know, are you not doing your homework? Are you relying on other people too much? Whatever it is. Okay, so write a function named list of divisors that takes a number as a parameter and returns a list containing all of the numbers that evenly divide that number. All right, so we probably want some helper functions here. So we may be a helper function that just determines if one number is evenly divisible by another number. So, you know, we want to know if I have a number, is another number evenly divisible by that? So let's just define a is evenly divisible to be a lambda that takes an A and a B. And what is that, modulo? So it's going to be equal modulo A, B, 0. That'll return true if A divided by B has a remainder of 0. Well, I don't know, it's possible, but I mean, I didn't assume that you were going to run it. Yeah, so I mean, I might have given you mod. I guess I'm going to run this, so maybe I said in the instructions that it was mod, but I think the actual function that exists is called modulo. Yeah, and like I said, I didn't assume you were going to run these, so I graded that with the understanding that there could be a missing parenthesis and that kind of jazz. All right, so if I want to test this, so is evenly divisible, and I want to say 9 and 3, for example, I get a true. 9 and 4 should give me a false. Something like that. So I can find out if the first value is evenly divisible by the second value. Okay. Now, the question we're having to answer here is, we're going to write a function that takes in a number and it gives you all of the values that are evenly divisible by that number, including itself. I'll give itself as an example. So if we take in a 9, it should be 1, 3, and 9. So we're going to check all the numbers from 1 all the way up to and including the final number. Asking each number along the way if it's evenly divisible. If it is, we'll count it on. If it's not, we'll just move on to the next value. So list of divisors. So define list of divisors to be a lambda that's going to take in, and let's see, we could build it backwards towards a 1. Well, let's look at that. That's going to take in a number, and it's going to return a list of all the values that evenly divide that number, including that number itself. So we want to count down to a 1, right? So we're going to go ahead and we'll we'll write a cond. So if equals num1, we're just going to boil down to 1. Otherwise, because we know 1 will evenly divide it. We don't need to ask the question, right? So otherwise, we're going to say if num and let's see, we probably want to call this list of divisors helper, because this is going to take in num and num, let's say. This will let me go through it forwards. So you'll see how I'm going to call this guy if I were to call it. So I'll say define list of divisors to be a lambda that just takes in a number. And what it'll do is it'll return list of divisors helper, passing it that number, and I can pass it I was going to count down. Maybe I'll just count up then. That's fine. So I'll pass it that number and a 1 to kind of get the ball started, get the ball rolling. So then the question I'll ask here is if current num is equal to num. If that's true, our final thing will be num. So like our example 9, I'll boil down to the 9. Otherwise, if I'm not at the end yet, then I want to ask the question if is evenly divisible num num. If that's true, then I want to cons num onto the result of calling list of divisor helper on num and minus num1. That's if it is evenly divisible. If it's not evenly divisible, I just want to call list of divisors helper, passing it the current num, and still the next guy to test after that. Okay, so if I pass in a list of divisors for 9, two R's, Clancy.
I was going to apologize before you even corrected it.
Where were you?
Yeah, I was going to.
Let's see, this guy is saying undefined, modulo is undefined for 0. Oh, this is like a divide by 0 issue, like counting all the way down. Oh, hold on. I'm subtracting 1. I should be adding 1 because I'm going from the beginning, right? I was originally going to go backwards. Now I'm going forwards. Killing me. Cons, but receive 3. And the last element of this guy has to be a list. So this should be the list of that num. All right. And like I said, you were writing it without the benefit of the interpreter. So things like that, you wouldn't have lost stuff for. So roughly speaking, you had to check to see if you had to know what evenly divisible meant. And then you would have, whether you wrote it with a helper or wrote it something else, or just had given me, reasonable pseudocode-y, whatever was fine. Okay. So next one, write a procedure called Fizzbuzz that takes a number as a parameter, returns Fizzbuzz if it's evenly divisible by 3 and 5, Fizz if it's evenly divisible by 3, Buzz if it's evenly divisible by 5. and the number itself. Otherwise, this one was pretty easy. I think most people got this one right. You know, I think pretty much anybody who answered it got it right. If you didn't answer it at all, then, you know, you should determine why you're not answering the programming questions. Write a lambda expression where variable x occurs free and variable y occurs both free and bound. Okay, so that's going to be something like, so we need x occurring free. So maybe we have an app expression where x occurs free. And then we have a variable y that occurs both free and bound. So then you can have a second app expression where y occurs free there, and then maybe you have y there. So that's occurring free and bound. So in this case, x occurs, it's not bound, so it occurs free. In this case, y occurs, it's not bound, so it occurs free. In this case, y occurs, but it is bound, so it occurs bound. This goes back to that lecture when we were talking about first, what does it mean to occur? And then where does binding take place? Okay, so I would say most people got that one right as well, as long as they had, I mean, I had some pretty crazy answers to it, but, you know, generally speaking, that one was fine. Conversion questions were fine. Grammar versus a production. I think most people did this okay. I mean, one issue, I'll just kind of throw it out there out loud, is, you know, I got some people that, you know, obviously went and, you know, whatever the book had for like an official definition of a grammar or procedure is, you know, so, I mean, I don't necessarily care that you go and look at the book, but I do kind of want to know what you know. And I don't know that any of you would have actually answered that question out of your own brain the way that some of the people pasted answers in there. You know, a grammar is a collection of rules that describe a language, right? And a production is each one of those rules. That's what it is. So, you know, I got some answers that I don't know that anybody could explain, because the book reads kind of like stereo instructions. So, you know, use your own brain for these things to make sure that you understand what they actually mean. So let's see. Given the binary tree looks like this, it's either just an integer or it's a list containing a symbol and two binary trees. Write an example of a binary tree that includes, that contains 5 numbers. So this was just reading a grammar and writing something that follows that grammar. And I said that contains exactly 5 numbers. So we have a binary tree. The binary tree is either just an int or it's a symbol. So let's say maybe we have, here, I'll just say A, and then we'll have, I need to have B, then we'll have, does it allow me to have a empty? Well, it has to be a single number. So A, B, 1, 2, so that's 2 numbers in that tree. C, so this is a tree with a symbol. This is a tree. This is a tree. 1, 2 numbers. This tree has 1 number for its left subtree. Right subtree has 2 numbers. So there's a binary tree with 5 numbers in it. All right, proving you could read a grammar. All right. Given that same grammar, write a procedure called Sumtree that takes a binary tree as a parameter and returns the sum of all the numbers in the tree. All right, so this one was missed quite a bit. This is the skill of being able to go from a grammar to code that mimics a grammar. So what do they call it? Sumtree is a lambda that's going to take a tree as a parameter, and it's going to sum up all the values that are in that tree. So we can say if number, actually I'll just write it as a cond, number tree, boil down to tree. Otherwise, if it's not a number it must be the other form of our tree. Okay, and the other form of our tree is a symbol followed by a tree and a tree, right? So else we're going to add Sumtree on the first subtree, which is the car of the cooter. And Sumtree on the car of the cooter. Something like that. So taking a tree, if it's our production that is just a number, go ahead and just return that. Otherwise, we're going to add whatever Sumtree returns for the left subtree and whatever Sumtree returns for the right subtree. It's going to have its own recursive, blah, blah, blah. And then ultimately, we're going to add all those things together, and this will sum all the numbers inside the tree. Make some sense? Here we can. Oh, my symbols. So this should be 1, 3, 4, 5, 6, 7. So it sums up the things in the tree. Let's see. What was the purpose of storing a lambda expression in our variable environment? Well, this goes back to that idea of lambdas being an unnamed function. What's the purpose of a variable environment? To hold bindings of variables. So names associated with values. So having a lambda stored in our variable environment allows us to associate an unnamed procedure with a name. So we can have function calls inside of our language. Make sense? All right, so something that took me down towards that path. Again, I got some weird copy and pasted stuff. And I got some made up stuff too. But so we can make function calls. Let's see, write a procedure called apply GD that takes a list of positive numbers as a parameter and returns a new list of the same length with every number replaced by the largest integer value that evenly divides it. Okay, so we need to get the largest value that evenly divides a number as our starting point. So we probably want to start with that number and walk backwards, right? So we'll say define largest divisor to be a lambda that takes in a num and we'll define largest divisor helper to be lambda that takes in a num and a kernum. Stop that for right now, and this guy will call largest divisor helper, passing it num and actually, depending on how you read this, write a procedure called apply GD. It takes a list of positive numbers as a parameter and returns a new list of the same length with every number replaced by the largest integer value that evenly divides it. All right. I think a reasonable person could read that and say the largest number that isn't itself. Although technically you could just say it's the number itself and probably make a reasonable argument, but I'm gonna write it the way I think it was intended. So largest divisor helper. So we'll start off by trying the number -1. You actually don't need to try that one. You probably only need to go down to half of that, but this isn't gonna hurt anything. We'll just do some extra passes. All right, so Largest divisor takes in a single number, and it's going to call the helper on that number and then start trying the number right below it for whether it's evenly divisible by it. Because remember, the job is we're going to try to find the largest number that evenly divides it, knowing that we will have a stop case, right? We know that we eventually get down to 1, and 1 definitely evenly divides it. So inside here, we'll go ahead and we'll have a cond. We'll say equal Kernum 1, that'll boil down to a 1. That's our answer. If I'm down to a 1 and I haven't found anything that evenly divides it better, then we're going to go ahead and just, here's your 1. That will evenly divide it. All right. Otherwise, if it's not a 1, we want to ask the question, modulo, or more than likely you probably wrote mod, because that was what I'd given you on the exam, but whatever. Modulo num kernum, and we want to find out if that guy is equal to 0. That means it evenly divides it. If it is, we will boil down to kernum. Else, we're gonna call largest divisor helper on num and minus kernum 1. Okay, so that's largest divisor helper. Now, what we're actually writing here is we're calling apply GD, that takes a list of numbers and replaces each element of that list with the largest value that evenly divides it. Apply GD, be a lambda that takes in a list of numbers. I just call it LON. And what this guy will do is it'll map largest divisor across list of numbers. So 7, 7, 1, 12. And if you didn't recognize that you could have used map here, you certainly could have written it to just process through the list and call the function on each element. Okay. So this wasn't necessarily testing map. It was more testing a more complex question. All right, questions about any of the individual. If you have a grading question, catch me on Slack or something. But if you, any questions about any of the individual questions on here? Okay. And like I said, the grades were fine. The big picture, you either did pretty well or you basically didn't earn points. It was one of the two. There weren't like middle of the road, there might have been one middle of the road test, something like that. Like I said, I think the low grade was like a 14, something not good. Remember my policy though, if you do better on the final exam than you do in the midterm, you can replace your final exam score with whatever you got on the midterm. No harm done, but hopefully this is at least a wake-up call for what you know and what you don't know, that kind of stuff. Okay, so then for last Thursday, we were working on hopefully you saw there was some comparisons to the things we had been working on in class, even though it felt like we were making a game. Most of you, I think at some point, probably in 300, if you took it with me, we implemented Towers of Hanoi. We might have actually done it in year 250 with Android, right? But usually I do Towers of Hanoi associated with a stack data structure, okay? And we're going to be starting to work with stack data structures here pretty soon. We start looking at our variable environment dealing with scopes. So that was kind of the let's give you something kind of like how you know, if you need to give your pet medicine, you hide it in its food. That type of thing. My wife does it with me all the time. It works. So Nice thing of chocolate pudding, she just puts whatever in there. I get yelled at when I start eating the plastic. Not even kidding. I should have some sort of like streaming service of like what happens in the Lippman household, because so many of these things are not even lies. I sit there for hours watching movies with Mr. Gonzalez. He's his own chair. Oh, it's bad. One day though, I'll be a memoir. So let's look at that lab here. And actually, I think from the exam perspective, the couple of you that I'm very concerned about, we've already had discussions. So, and I think that we have a game plan. So I think everybody is relatively okay, and you probably know why you sucked or not at this point. So that's the punchline. Okay, so I'll go ahead and copy this. We'll open it, but hopefully some of you have seen this before, but we weren't actually playing the game here. We were more working with the constructs. So, you know, there's this thing called Towers of Hanoi where we have this idea of a tower, and a tower is a collection of discs where, you know, discs can move from one tower to another tower, but it has the rule that a larger disc can't go on top of a smaller disc. So, you know, we have to play the game to get ultimately all the stuff over onto the far tower and hopefully the minimum amount of moves, but you know, that type of thing. Okay. So in any case, what we were supposed to do is we're going to implement constructors and modifiers for our Tower of Hanoi game, not actually the game itself. So in the game, there exists a collection of 3 towers. So probably a list of towers, something like that. Okay. A tower, though, is a collection of discs, but it functions like a stack. Okay. And the presumption was you knew what a stack was. A disc is a representation of a single disc of a particular size, perhaps represented as a number. Okay. So we want to go ahead and create constructors for our disc. All right. So we'll go back out here. So I'll define disk to be a lambda that takes in a size, and it boils down to, now you can decide how you want to implement this. I think by my example here, I just do it as a number, right? So this is a disk, this is a disk, this is a disk. So the constructor for it is going to boil down to just the size. Okay. Then we have the idea of a tower. And a tower, when it's initially created, it's going to boil down to the empty list. There's nothing in it. That's an empty tower, right? So you could call it empty tower if you wanted to. That's a constructor for an empty tower. Or we can have modifiers for a tower like add disk to tower, something like that. But you know, anything reasonable here is fine. All right, so we have a tower, and this could be a collection of up to 3 disks. Right now, it's just going to be a collection, but it's going to function like a stack. Okay, so now create the following functions. We have a init game, which creates our initial representation. So our initial representation should give us something that looks like this. Okay, but we want to do that in terms of our constructors. So inside here, we're going to go ahead, we're going to define init game, or whatever I said, to be a lambda that takes in no parameters. And what this guy is going to boil down to is he's going to boil down to a collection of 3 towers, with the first tower having some disks added to it. Okay, let's go back here for a second. So we have this idea of make move. Now we can make the assumption that our initial towers have some stuff added to it. But what I'm going to do is I'm going to go ahead and I'm going to write a modifier called add disk, where we try to add a disk to a tower. So we'll put that here before this. We'll say define add disk. This guy will be a lambda that's going to take in a tower and a disk. And it's going to attempt to return, well, it's going to return a tower, either the modified tower or a tower without that disk on it. It actually might be beneficial for us to have it return a Boolean if it doesn't work, and the modified tower otherwise. Okay, so we could say something like if disk, which we know a disk is just a number, right? We could have getters for disks like get value, but we know it's just a number. So, you can decide how far down the list you want to take the abstraction. So we can say if, now we want to be able to get the top of the tower. Now towers operate as what? Stacks. So stacks typically have peak, push, pop, right? Those are the functions that a stack has. So if I just want to look at the top of the stack, I'm doing a peek, okay? So we want to create the ability to look at the top of a tower. So define check top. Maybe we call it that, or you can call it peek if you really want to. And what does check top do? It takes in a tower, and it's going to return the car of that tower. Okay, but only if the tower actually has something in it. So we might want to ask the question, if null tower, then return false. Otherwise, return car of tower. So we could try to check the top and fail. Something like that. All right. We could have a, already working on add disk. So add disk takes in a disk, and now we're going to say if check top tower. Now, we might be interested in whether or not a tower is currently empty. Now, we could write a second thing, otherwise we know towers are lists, right? So we could actually now turn this into a cond. So we can say cond null tower. If that's the case, then we know we can safely add the disk, right? So what will we do? We will cons disk onto tower. No rules to follow there, right? Okay, so if the tower's already empty, I can just go ahead and whatever disk you gave me, I can put it on top of the tower. All right, now if it's not empty, then I know I can safely check the top. So I don't actually need to use this false, but it's probably not bad logic to go ahead and have the ability for us to get a Boolean out of there. So I know if I'm in this position right here that I can conveniently, I can accurately check the top of this tower. So now I want to know I'm only allowed to put smaller disks on top of larger disks. Okay. Let me just make sure that make move. Yeah, the make move is the one that we're effectively doing. So I'm calling it add disk, but we're really calling make move. So we're writing make move here. So make move attempts to move a disk onto a tower, and either succeeds or doesn't, something along those lines. Okay, so if the tower is null, I can do it. Move is made. If the tower is not null, then I want to check top of tower, and I want to compare that to my disk, and only if my disk is less than the top of the tower, then I can cons the disk onto the tower. If the thing I'm trying to put onto the top of the tower is smaller than the top of the tower itself, the current top of the tower, I'm allowed to put it there. All right. Otherwise, I can decide when I want to return here. I can return the original tower. I can return a false. It didn't work. I'm going to go ahead and return a false, at least for now. I mean, you can make arguments probably different ways. So we make a move and the move's either successful or it's not successful, something like that. All right, so that's how we would make a move, and the move is only successful if something like this happened. Okay. Let's see. Oh, and I even told you if it's not legal, boil down to false. Otherwise, it should return the modified game board. Oh, so actually make move is something that happens to the entire board. So it's going to take in a game board, the source tower number, and the destination tower number. Okay, so that's fine. So we can go back to what I was writing here called add disk. So that guy attempts to add a disk to a single tower, and it either works or it doesn't work. Now we'll take in, we'll say define make move, and this guy will be a lambda that takes in a game board, a maybe a source and a dest, something like that, 3 pieces of information. And we need to go ahead and get the tower from the source, get the tower from the dest, and ultimately get the disk that should occur there. Now, it wouldn't have been unreasonable for you to assume that making move is taking in a legal move. Well, an attempted legal move, meaning that if you choose tower 3 and there's nothing in tower 3, that's not a move. You can't say I'm sourcing from something that has nothing. But you could put a bunch of error checking to make sure that your source actually has a top. You know, so you can say, you know, if check, if I guess you would have to say if check top is not equal to false, then you're allowed to make a move. Traditionally, we would say maybe you don't have to do so much error checking. So we can assume that source and destination are legal places. And if I chose something as source, there is a disk there to try to make a move with, but it might not necessarily be a legal move when I go to put it onto my destination. So source is a tower. So I'll go ahead and maybe do this as a let. So we'll have source disk is equal to, now check top gets the top of a tower, but we also want to have a situation where we can get a disk from a tower. So we're going to actually be rebuilding our towers here as well, right? So when I make a move from one tower to another, I get as a result a game board, and that game board could have, well, may have a modified board. If it was a legal move to make, I should now have a new set of distribution of disks in my towers. Okay, so the source disk, we'll just kind of take this one piece at a time. The source disk is going to be the check top of my source tower, at least for right now. All right, so that's my source disk. That's the guy I'm going to be trying to add to the other tower. Okay, now what I want to try to do is I want to add a disk to that other tower, but I need to make sure that this guy doesn't give me a false. So I kind of need to check it and then actually do it. So I kind of need to you actually call the thing twice. So I'm going to do this as a let star. That way I can use things from earlier on. So then I'll say check. Let's call this guy dest check is going to be add disk. Which tower? To the dest tower. Which disk? The source disk. All right, so destination check is going to have a value associated with it. It's either going to be my updated tower or it's going to be a false. If it's false, the move wasn't legal. Okay, so I want to check to see if it's equal to false. So cond equal dest check false. Okay, if that was the case, if I wasn't able to take it to the destination, what do? I just boil down to our game board, the original game board. No changes have occurred. Otherwise, I need to have a game board that is modified from the original with source and dest being different than they were before. Now, the issue is that source and dest are part of our game board. Actually, source is an index, right? Is that how we treated source as an index? I think I said that instead of a tower itself. Make move takes a game board, a source tower number, and a destination tower number. Okay, so we actually can't say source. We actually need to say game board. We need to get it from a position. So we do have a function called listRef that lets us do that, but I'm going to actually just write a quick function. Define get tower to be a lambda that takes in a game board and an index. If index is 0, I can go ahead and return the car of game board. Else I want to call get tower, passing it the same game board and minus index 1, and it's not going to be the same game board. This is going to be the cooter of my game board. Okay, so that'll allow me to extract a tower from my game board. So I could say, give me tower at bucket 1, give me tower at bucket 2, something like that. So this is get tower. So we're going to call this guy source tower. It's going to be get tower from source. Dest tower is going to be get tower dest. All right. Now, what will be helpful is I really need to get the other tower, the tower that isn't the source or the dest in this case, because I'm going to need to rebuild my my game board after I have my towers updated, right? All right, so to do that, I need to maybe have a function that takes in those two numbers. Now I know my tower only has, my game board has 3 towers in it. So if the two things are 1 and 2, or 0 and 1, I should return a 3. If it's 0 and 2, I should return a 1. If it's a 0 and 1, I should return a 2, so on and so forth, right? So I need to map from, I need to know what's the index of the tower that I'm currently missing, all right? So it's kind of a funny function that's only really usable for this particular thing, but given 3 towers, give me the odd man out, the one that isn't already selected, okay? So, this is actually kind of an interesting, this is an interesting problem. There are some trying to think if there's a super shortcut to it. Okay, so one thing I might do for this is if I want to get the tower that is the odd man out, I might have this idea of remove tower from an index, but from multiple indexes. So, but really what I want to do is I want to mark the towers that I want to remove. So let's say I want to define get other tower to be a lambda that takes in a game board. It takes in a index 1, index 2. And now it should give me the game board that lives at the other indexes. Is there something better than just a series of if statements? There might not be. Because index could be 0, index 1 could be 0, index 2 could be 1, or vice versa. And then we should turn a 3. It could be 1 and 2, we should return a 0. It can be 0 and 2, we should return a 3. Doesn't seem like a very elegant solution. There's got to be a better solution than that. There's 6 permutations. So you can definitely solve it with, a series of 6 if statements, or 3 if statements if you use ors. I'm thinking about something like more magically, something more interesting with that scheme would let us do. Okay, so I can say it doesn't help me. Oh, whatever. All right, I was trying to be fancy with it. It would have been more fun. All right, so if index 1 is equal to 0, and, well, here I'll say index 0 here. Index 0 is equal to 0, and index 1 is equal to 1. If that's true, or the other way around. So if either of those things are true, then I want to return a, now the number is 2. So we probably want to get tower. So I want to return get tower game board 2, like that. Otherwise, or 1 and 2, or 0 and 2, or 0 and 2. Then I want to return 1. And then I can just have an else. Else get tower game board and 0. So that will get me the other tower. Okay, and I'm going to put, I think, Dr. Scheme might let you put these things wherever, but I'll put this before make move. All right, so I have my source tower, I have my destination tower. Now I need to get my other tower. That's going to be get other tower game board source and dest. Now I have my 3 towers. Now at some point I need to make sure I put them back together in the right order, right? But I do have my 3 individual towers. I will have my the source disk, I'll have my destination check. So if my destination check is false, I have the easy mode where I can just return the original game board, nothing happened. That part's easy. All right. Otherwise, if a move can be made, then I need to make the move, but I need to put the towers back together in the right order. All right. So I probably want to have a easier way to put them back together in the right order. This is one of those things where object-oriented programming makes life a lot easier, right? All right, so let's call this guy define reassemble. Going to take a lambda that's going to take in a call this guy an A. T1 index, T2 index, T3 index. Which actually means that it's helpful to have the correct indexes of these guys, not just the tower from the get the other tower. So list 2 and get that guy. List 1. So I'm building an object, packaging it up, and then list 0 and this guy. So then get, so the other tower is going to give me that object. So I'll just make sure I'm working with it here. So this guy gives me a list containing 2 elements. So let's call it other tower object. So now we'll say other tower index is equal to other tower object, carve that. Other tower, the actual other tower will be the catter of other tower object. All right, so now I have all 3 indexes and I have all 3 towers. So now I have all the pieces I need to reassemble this guy. So if a move is allowed, then I want to go ahead and I want to else I want to get my modified source and destination tower. So I'm going to put those guys in a let. I think let star might be needed. We'll see what I come up with here. So I want to set we'll call this new source tower to be equal to my cooter of source tower. That's my new source tower. My new dest tower will be the add disk to which disk? The car of my original source tower. And is it the disk or the tower first? Add disk, it's the tower first. Okay, so that's my new destination tower, is the result of calling add disk to my destination tower, giving it the disk from the top of my source tower. Okay, so my new source tower is the rest of my old source tower. My new desk tower is the add disk to my desk tower of the disk that was at the top of my source tower. Okay, so those are the two things that I'll need. So now inside here, I have made my modifications to my individual towers. Now I need to reassemble my, I guess the stuff, right? So is there a better way than just an if statement? Yeah, I think so. So we'll call reassemble. Reassemble is going to take these guys in as a parameter. Now, actually, what I'm going to actually do this. I'm going to have the methods return something a little different here. So it's going to be, I'm going to call reassemble. And I'm going to pass it a list of towers and a corresponding list of indexes. So this is going to be new source tower along with source. Actually, sorry. New source tower, new desk tower, and other tower. I'll create a list out of those guys. And then I'll also create a list out of source, desk, and other tower index. So now this guy will take a list of towers and a list of indexes. Okay. Now, what I want to do is, as long as these two, I want to modify these lists at the same time. As long as these lists have something in it, I want to keep finding the smallest index. Because I'm ultimately going to build a list of towers out of this with the smallest index coming first, the next smallest index, the next smallest index. So I'm going to have a defined find smallest to be a lambda that takes in a list of towers and a list of indexes. And he's going to go ahead and he's going to go through this looking for the smallest index in the corresponding tower. So I actually have to probably sort this. And we don't have time to do that in the next minute. Yeah, Scheme really does suck for this problem. I mean, it's not that it's hard, it's just tedious. To do every piece of it, you have to like ask a zillion questions. So looking back on it, what probably would have been helpful is to create abstractions that would allow me to treat lists like they're arrays and swap elements in a list, kind of like the swapper thing. If I would have created constructs for that, then I could just say, I would never actually have to take them out of order. I could always just say, give me the tower source, give me the tower destination, change it and replace bucket 1 with the new tower, replace bucket 2 with the new, updated tower. So I think 2 abstract methods before that would have been beneficial. Interesting. All right, so for homework, and this is actually somewhat on topic, but somewhat off topic. But I think it's something that's going to benefit all of you. You'll probably find it fairly easy in here, or at least you should. This was brought up in another one of the classes. There's a website called codewars.com. And it's basically kind of a training facility and then kind of a online hackathon-y type thing for writing software. But one of the things that is sometimes challenging for students who want to work on their programming skills is it's hard to come up with little problems to work on, right? So what's kind of cool about Code Wars is you sign up and then it doesn't cost anything. And you pick the language that you want to train with. So you can pick your favorite language, Java, C#, doesn't matter. You're looking at problems to work on. You can always work on them outside of their little thing. But then what it does is it gives you training. I've only messed with it a little bit. So at least from a training perspective, it gives you a problem. So, and then you can try to solve that problem and test it and submit it and things like that. So you end up having a whole bunch of solutions. Now, the hope is that you run into, especially as people in this class, you run into several problems that you are able to solve relatively simply. So I'd encourage you, so for the assignment, I want you to create an account on Code Wars, and I'll put this up on Blackboard so you can read it on there, but create an account on Code Wars and do at least one submission in a language of your choice. I don't think Scheme is on there, so it doesn't really matter. This is more just guaranteeing you have access to this tool. And submit a screenshot of like that solution that you did working. Honestly, I'd encourage you to maybe do several solutions to run into something that you feel like challenges you. But at the very least, this will introduce you to a tool that it will be good for practicing stuff. Make some sense? All right, so then on Thursday, we'll bounce back to starting to look at scoping rules and continue to add stuff to our language, but we want to pretty quickly get to dealing with storing functions and things like that into our language. And also we want to implement recursion. All right, I will see everybody on Thursday.